In this video, we're going to dive a little bit deeper into the MO theory of bonding. So we saw that atomic orbital theory predicts that two bonds overlap, and the overlap itself is the bond. It's localized, the electrons are localized to the atom still, and it doesn't really move off of the atoms. So we saw that if we have a single bond versus a double bond versus a triple bond, we can predict the types of bonds that form using knowledge from Gen Chem. So we see that a single bond is going to be a sigma, a double bond is going to be a sigma plus a pi bond, where the sigma bond forms first, and the triple bond is a sigma plus two pi bonds. So atomic orbital theory says that these electrons are localized, where MO theory, which is what we're more interested in, tells us that these are delocalized, and they're actually delocalized over the entire molecule in itself. It's important to talk a little bit, before we talk about how these orbitals form, to talk a little bit about the physics behind this. So when we have, it's very useful to talk about electrons as waves in this case. So let's say we have a wave that looks like this, and this is our baseline here. So this is an electron. It's behaving as a wave. It has an amplitude and a frequency. We would say that this point right here, we would call this a node, where it has zero amplitude. And we would say that it has a trough and a peak, and some kind of wavelength and frequency. If we were to add this wave to itself, say we were to add this wave to itself, right, have the peaks match up, the nodes match up, and the troughs match up, we'd have this amplitude plus this amplitude, which would be double. So we have a wave with double the amplitude. And then we'd also have a trough that has double the amplitude in the negative direction. We would still maintain that node right in the middle, no amplitude. And now we'd have 2 times the amplitude in both directions. When we have waves adding up in a positive manner, positive meaning it's getting larger, we call this constructive interference. Constructive meaning they are additive. If we look at the opposite case, let's say we had the same wave that we started out with before, and we add it, or we add it to a wave that is opposite in phase, we would call these two waves out of phase, where we have amplitude A plus amplitude negative A, we have negative A plus positive A. We would see that this wave is zero all the way across. So when waves add up and get larger, we call it constructive. When waves are the opposite and they are actually subtractive from one another, we call this destructive interference. Now, destructive doesn't always have to be to zero, just like constructive doesn't always have to be twice the amount. In reality, it's some combination of these two usually, but we're either approaching zero or we're approaching double when we're doing constructive or destructive interference. So let's talk about what this looks like for specific orbitals. So say in the most basic case, say we're looking at a 1s orbital, just like we looked at before. This is 1s for hydrogen, and we have 1s for hydrogen. Now these are in the same phase. When we're drawing orbitals, I'll either color it in to indicate opposite phase, or leave it blank to indicate the same phase. So these are both blanks, so these are in the same phase. So we'll know when we bring these together, we will have constructive interference. So atomic orbital theory says that these two orbitals just overlap, and they don't really do anything else. The electrons are localized to the individual hydrogen atoms. However, molecular orbital theory says that there's going to be mixing. There's going to be constructive interference where these two orbitals overlap. So this is actually going to get much larger in the middle, and it's going to kind of trail off at the side. So what our overall molecular orbital would look like is we have something that's large in the middle and smaller on the side. So we get kind of this football shape that occurs. And this is what our sigma orbital looks like. So it's large in the center and kind of smaller off to the sides. So this is what our sigma orbital would look like. Now, statistics tells us that not every instance where these two hydrogens come together will they be in the same phase. Now, we may get cases where they are out of phase. So what would that look like? So let's say they come together. We have this colored in. Now, right in the middle, right here, we see we have a colored in and a non-colored in section. So this is going to be that destructive interference right in the center. So if we have plus and minus and they cancel each other out, we're going to have a node right in the center. So we'll have a node right down the middle, and we'll have some kind of lobe on either side, where this one is colored in still. To label this, we call this a sigma because it's derived from the same orbitals that form a sigma bond, but we call this sigma star. Sigma is going to be our bonding orbital, and we call this sigma star anti-bonding. So every pair of atomic orbitals, because remember, for two atomic orbitals, we're going to generate two molecular orbitals. So when we have two atomic orbitals come together, we're always going to generate this bonding anti-bonding pair, and that's uniform for all types of molecular orbitals that form. So this is how a sigma bond forms. Let's look at how a higher order bond forms, like a pi bond. So sigma bonds form when just two lobes come together. So that can be an S plus an S, that can be an S plus a P, or that can be two P's that come together head on. So all of these would form sigma bonds. Now let's look at pi bonds. So pi bonds, as we know, are what happens when two p orbitals come together. So, and I'll color this. Remember, we have a phase change down to the other lobe. Atomic orbital theory says that these will kind of, and I'll make these bigger just for our drawing purposes. These are going to overlap, and in the middle, this is all colored in. You can kind of already see what the pi orbital is going to look like, but I'll just draw this. So we have constructive interference here and here. So what we get is kind of these dual lobe type things, two hot dogs on top of one another, where one of them is out of phase of the other. This is what our pi orbital looks like, and this is, just one line, this is our bonding variant. And note, we have a node right in the center of our p orbitals, so we're going to have a node right down the center of our pi orbital as well. Now, if these are out of phase with one another, say we have one pointing up and one pointing down, when these atomic orbitals come together, and I'll kind of draw these suggestively, we have this colored in, and we have this colored in. So you'll note that we have destructive interference appearing here and here. So when we draw, you can already predict, it's called our pi star orbital. We're going to have a node, not only our node parallel, but our node perpendicular right down the center. So we have a node right down the center, just like we had in our sigma star orbital. And we have these lobes that kind of look like they're pushing away from one another. And let's see, this one is colored in, and this one is colored in. So we have two nodes in the pi star. So this is a node, and this is a node. And we would call this our pi star bond, or pi star antibond, rather. So we have our pi bonding and our pi star antibonding. These always come in pairs, just like the sigma and the sigma star come together in pairs. Just remember when bonds are forming, the atoms are moving together to maximize the attraction. So that is the attraction between electrons and protons, or electrons in the nucleus, and minimize repulsion. So that's going to be the electron-electron repulsion and the proton-proton repulsion in the nucleus. So all of these antibonding formations are going to be appearing at a well. So if we look at an energy diagram of you'd say two atoms brought together, as we move, as we start out where we have two atoms very far apart, so this is HH. And as we move closer, we're kind of dropping in energy, and then we hit this well. This is where our bond forms. This is the minimization of our repulsive forces and the maximum of our attractive forces. And then as we get closer and closer together, we're going to spike up in energy because now we're increasing the repulsive forces between the electron-electron forces and the proton-proton, or the nucleus-nucleus repulsive forces. So this is going to be if they're really close to one another. Again, if these are far, we feel nothing. We eventually form a bond, and then as we get too close, we are pushing these two atoms a little bit too close together, and we form an unfavorable situation once again. So let's look at the example of hydrogen again. So when we have an H atom plus an H atom, We're going to form a HH sigma bond. We already know that 2 AOs means we're getting 2 MOs. We already see that our MOs are going to be a sigma plus a sigma star bond. So let's draw a diagram that represents this energy, or the energy levels of these two bonds. So we have a 1s orbital with 1 electron in it. We have a 1s orbital with 1 electron in it. Now our sigma are coming together. As we saw, forming a bond is always going to be lower in energy than the individual atomic orbitals as they are separately. So our sigma bond is going to be stabilized. So our sigma bond is lower in energy than our atomic orbitals are. So we can trace this down. Our antibonding orbital, however, is destabilized because we've done destructive interference and we formed a node right down the center. So our antibonding orbital is always going to be higher in energy than our individual orbitals. So this is going to be up higher in energy. We always, the Heisenberg uncertainty principle and the Pauli exclusion principle tell us we're always going to fill from the bottom up. We have 2 electrons, so we're going to fill 2 electrons into the sigma bonding orbital. And let's predict what the bond order, what type of bond are we expecting for an HH bond? Remember that bond order is going to be the number of bonding minus the number of antibonding electrons, that is, divided by 2. So in this case, we have 2 bonding electrons minus 0 antibonding electrons divided by 2, which would give us a bond order of 1. And this is why HH forms a single bond. It has a bond order of 1, which means that it's going to be a single bond when it forms. Now let's look at an example where this doesn't happen. So there's a lot of, this MO theory can give us a lot of insight into why certain things form and why certain things do not. So let's look at an imaginary compound, He2. So let's draw the molecular orbital diagram for He2. So He2 has the orbital notation 1s2. So again, we have a 1s orbital, so we have 2 there. We have a 1s orbital, 2 there. We're going to form a sigma and a sigma star. Sigma and a sigma star. We're going to just draw these dotted lines showing that the sigma star is up in energy and the sigma orbital is below in energy. And now we're going to fill in our electrons. We have 4, so we go 1, 2, 3, 4. And if we look at the bond order, we do bonding, which is 2. We have 2 electrons in the bonding orbital. Then we have 2 electrons in the antibonding orbital over 2. 2 minus 2 is 0, so our bond order is 0. He2, which we could predict might look like this, does not form because we have a bond order of 0. It would be destabilizing to cause this to form. So this really only forms under very high energy, say laser or high vacuum situations. So under normal conditions, we will not see this molecule form because molecular orbital theory predicts we have a bond order of 0. It will not form a bond. That would be destabilizing. Let's look at one more example that's a little more complicated. Let's predict what O2 is going to look like. Again, this is 1s2, 2s2, 2p4. And in this case, I'm only going to be looking at the 2p4 situation. So I have 3 orbitals in that case, 2p, and 3 orbitals over here, 2p. They have 4 electrons, 1, 2, 3, 4. 1, 2, 3, 4. And since we have six orbitals, atomic orbitals, we're going to form 6 molecular orbitals. So we have 3 down here and 3 up here. Now, whether the sigma or the pi bonds are higher in energy or lower in energy is beyond the scope of this course, but we can just say this is sigma plus 2 pi, and this is sigma star plus 2 pi star. So oxygen, in theory, could, in theory, form a triple bond. But let's see what the bond order is and examine what kind of bond forms an O2. So there's 8 electrons total, 4 on either side. So let's fill them in. We have 1, 2, 3, 4, 5, 6, 7, 8. Let's examine the bond order. So we have 6 electrons in our bonding shell. We have 2 electrons in our antibonding array. Divided by 2, we have 6 minus 2, which is 4, over 2, which is 2. So this tells us that, indeed, oxygen has a double bond. And if we examine the Lewis structure, we see, sorry, that's an oxygen, not a sigma. We see that the most stable configuration of oxygen will have a double bond, and it has 4 lone pairs around it, which will correspond to the 2s2, 2 by 2s2, and then 2 lone pairs from here. So this is a good predictor. Again, it's a sigma plus a pi bond. This is a sigma plus a pi bond. So molecular orbital theory is a really powerful tool if we're trying to examine bond order, if we're trying to examine whether molecules form, and if we're trying to understand the specifics of the bonding around a particular set of atoms in a molecule.